This is part 2 on the topic applications of HSAB principle for visually impaired students. Pearson's principle of HSAB has a number of applications in inorganic chemistry. Some of these are discussed below. First, stability of the complexes. We have already noted that hardness and softness of acids and bases are related to only the hard and soft interactions. Hardness and softness of acids and bases has nothing to do with the inherent acidic or basic strengths of the acids or bases. For example, both OH negative and F negative ions are hard bases, although OH negative ion is for stronger a base than F negative ion. In fact, OH negative ion is 10 raised to the power 13 times more stronger base than F negative ion. However, in HSAB principle, both OH negative and F negative ions are at par with each other. Pearson in 1963 explained the relative stability of coordination complexes on the basis of HSAB principle. Let us consider a general reaction between a Lewis acid and a Lewis base. A plus B gives AB. The complex AB will be most stable if A and B are either both hard or both soft. The complex AB will be least stable if A is hard and B is soft, or A is soft and B is hard. For example, a complex between a soft acid Ag positive and soft base I negative ion is quite stable in contrast to the one between a soft acid Ag positive and a hard base F negative. Ag positive plus 2I negative gives AgI2 negative, soft interaction. Ag positive plus 2F negative gives AgF2 negative, soft hard interaction. Similarly, the reaction between lithium iodide and cesium fluoride resulting in the formation of lithium fluoride and cesium iodide constitute an instructing example, suggesting the preferential stability of soft and hard combinations. Some of the other important reactions suggesting the stability of the soft and hard interactions are given below. Copper iodide plus copper fluoride gives copper fluoride plus copper iodide. Calcium sulfide plus water gives calcium oxide, thus hydrogen sulfide. Beryllium iodide react with mercuric fluoride to give beryllium fluoride and mercury iodide. The rule of thumb in determining the stability of the complex is the preferential formation of hard and soft interactions. Exercise. Why COF6 3 negative complex is more stable than COI6 3 negative? Solution. In both the complexes COF6 3 negative and COI6 3 negative, the oxidation state of cobalt is +3. Cobalt 3 positive is a hard acid, therefore its combination with a hard base, that is fluoride negative, will lead to cobalt fluoride 6 3 negative, which is a hard interaction. On the other hand, combination of CO3 positive will give with the soft base I negative will lead to COI6 raised to the power 3 negative, which is a hard soft interaction. Thus, COF6 raised to power 3 negative is more stable than COI6 raised to the power 3 negative. It has also been noted that the combinations of hard or soft ligands with a metal ion is always preferred over combination of a mixture of hard and soft ligands with a metal ion. For example, the complexes cobalt cyanide 5 iodide raised to the power 3 negative and CONH3 whole 5 F whole raised to the power 2 negative are far more stable, whereas the complexes COCN whole 5, F raised to the power 3 negative and CONH3 whole 5I whole raised to the power 3 positive are unstable. This is because Cn negative and I negative are both soft bases, whereas NH3 and F negative are both hard bases. 2. Classification of acids and bases. The acids and bases can be classified as hard or soft depending upon their preference for hard and soft reactants. Let us consider the following reaction. BH positive plus CH3HG positive in equilibrium with CH3HGB positive plus H positive. We already know that H positive is a hard acid, whereas CH3H positive is a soft acid. If B happens to be a hard base like NH3, the reaction on the left side will be preferred. That is NH4 positive plus CH3HG positive. Backward reaction CH3HG positive NH3 plus H positive. Conceptually, ammonium can be written as NH4 positive and in equilibrium with NH3 plus H, which means the formation of NH4 positive is preferred because of hard acid H positive and a hard base NH3. On the other hand, if B is a soft base like R2S, the right hand side reaction will be favored as shown. Conceptually, CH3HgCsR2 positive can be written as CH3HgSR2 positive in equilibrium with CH3H positive plus Sr2, which means the formation of CH3HgSr2 is preferred because of soft acid CH3Hg positive and a soft base Sr2. Similarly, an acid A can be classified as hard or soft depending upon the direction of equilibrium. AF negative plus SCN in equilibrium with ASCN plus F negative, where F negative is a hard base and SCN is a soft base. If A is a soft acid like Ag positive ion, then the above reaction in the forward direction is favored. Conceptually, AgSCN is formed through soft-soft interactions. Hence, according to HSAB theory, the reaction is preferred in the forward direction. On the other hand, if A happens to be a hard acid like Na positive ion, then the forward reaction is favored rather the backward direction is preferred.